last class we have been discussing on simple symbol table, and we have seen that the simple symbol tables they work well for languages with a single scope, and single scope means all variables and identifiers that we have in the program they are visible to the entire program. So, there is nothing like there are like if you have got local variables, then they are visible only within the function or procedure. So, that type of considerations are not there. So, all the variables and identifiers, so they are visible to the entire program. So, for this type of programming languages, it is we can have a very simple structure, and these are the alternatives, like we can have a linear table, we can have ordered list, tree or hash table. These are the commonly found symbol table organizations. So, one thing I would like to tell you that it is not mandatory that you should follow only one of these 4 alternatives for symbol table organization. So, depending on the programming language and the type of information that you need to store, so you may prefer some other organization as well. So, some complex data structures can be thought about, and then the symbol table may be organized like that. So, these are actually the commonly used options that we are exploring. So, next if we look into these different table organizations, the first one is the linear table. So, it is a simple array of records with each record corresponding to an identifier in the program. So, in the like here is an example, we have got a program where we have got these variables integer variables x and y, a real variable z, a procedure ABC, and we have got a label L1. So, for as far as the symbol table contents are concerned, so we are storing the name of the symbol or name of the identifier, its type and the location. Location is the offset from the beginning of the program. So, what we mean by offset, it is like this, that suppose we have got a program, say this program, it is now if you say that at the if you consider the corresponding object file, the object code that is produced. So, in that object code I should have space for this x and y. So, x is the first location that we have in the program. So, you can say that the offset of x is equal to 0, fine. Then after that we have got integer y. So, assuming that these integers are 4 byte long. So, these 4 bytes will be reserved for x. So, these 4 bytes are reserved for x, and after that the next 4 bytes it will be storing for it will have the y values. So, these 4 values, so they are corresponding to y. So, y's offset is this one. So, that is equal to 4. So, if you look in terms of byte offset, so it is 0, 1, 2, 3 and then y starts at 4. So, that way the offset of y is 4, and after that offset of z. So, offset of z is 4 plus size of y, the size of y is 4. So, z will start from this point and it will be spanning over next 6 bytes. So, if we assume that the real numbers are requiring 6 bytes. So, it will have 6 bytes. So, this offset is equal to 4, this offset equal to 8, and then we have got some statements here. So, it is taken as if we do not have any more definitions here. So, they are some statements are coming. So, so we can say that from this point onward the actual code for the program will start. So, from this point onward the code will start. So, accordingly we can calculate the offsets, like as we are converting this programming language statements into machine language. So, accordingly it will take few lines of the few bytes of the machine language program to store the corresponding source language statements. So, that way the offsets will be progressing. Now, when we come to this procedure ABC, so this ABC name is installed into the symbol table, its type is set as procedure, and the offset is from the beginning of the program after how much time, after how much byte this ABC is coming. So, if I assume that this translation goes up to this point, and then from this point onwards I am storing the procedure, the code for procedure ABC. So, this is the code for procedure ABC. So, what is the offset, that is starting from the beginning of the program. If I assume that this location is 0, so what is the corresponding byte index? So, that is the offset of ABC. So, the concept comes like this, because ultimately this program will be loaded into memory and when it is loaded, so a similar such image will get created onto the memory. So, they will be copied byte by byte from the secondary storage to the memory, main memory. So, there the offsets will be maintaining their relative positions, the variables that are defining the program statements that we are defining. So, they will be at relative offsets as it is there in this translated program. So, this procedure ABC, so we will have the offset of ABC stored here, then L1. So, after that again some statements are coming. So, they are coming here, and at some point of time this label L1 occurs, though in languages like C we are not having these labels much, but in some programming languages we have that. So, in C also these labels are allowed, but it is not encouraged. But anyway, so since it is there as an identifier in many programming languages, so it is also kept in the symbol table that L1 is of type label, and similarly we can compute the offset of L1 from the beginning of the program. So, that way all the offsets are calculated, and those offset values are stored in the location part of the symbol table. So, this is the linear table organization. So, this is simply an array of records, and each record has got 3 fields in it: name of the symbol, the type of the symbol, and the offset. So, so that way we can have this structure. Now, apart from this linear table, so other organizations are also possible, but linear table, if there is no restriction on the length of the string for the name of an identifier, string table may be used. So, what I want to mean is that this name part, so name part ultimately, so we are storing the name of the symbol. Now, if there is the programming language will tell whether these identifiers should have a finite length or not. So, if it is not finite, so in that case it is better that this name field, instead of being a character array, so it can be a pointer and it points to the string table. So, as I was discussing in the last class, so this string table, so it will have all the string variables, all the strings that are occurring in the program. So, here this so suppose for this x, so this it will be storing this x followed by the null character, and this pointer will be pointing to the this particular entry. Similarly, after that we have got the symbol y followed by null character. So, this will be a pointer to this y. So, we can have a situation like this. Similarly, at some point we have the name label procedure name ABC. So, it is stored like this A B C and then the null character, and then this this will be a pointer to this entry in the string table. So, this way using string table, so we can have we can store the variable names which are whose length is not restricted. So, if the programming language says the length of the symbols not restricted, then we can do that. However, in most of the cases we have got this length restricted. In that case, so we can have this simple character array as the name part. So, in that case when it is when string table is used, then the name part will be holding the pointers. The operations that we do on symbol table, as we said previously, that lookup, insert, modify and delete. So, if you want to search in the table, then it will take order n time, because assuming that there are n number of entries in the table. So, it will use a simple linear search. So, it will take order n time. Similarly, if you want to insert, then you need to go to the end of the table. So, assuming that you go to the end, so it will so that can be taken like that. So, then modification also it needs to search. So, so that will take order n time. So, insertion can be made order 1 by remembering the pointer to the next free index. So, if you remember what is the next free index, then it is order 1, because you do not have to search for a free slot in the table. Okay. So, if you are remembering the say one index, like how many entries in the table are full, in that case the next insertion is at the next free slot. So, that way it can be done in constant time. Scanning most recent entries first may probably speed up the access due to program locality. So, what we mean is that so, so program locality means that at any point of time, if I am having a program, so suppose I am at this particular line in the program. So, in this line, suppose it is accessing the variable x, then it is very much likely that in near future it will be accessing the variables which are close to x in the sense that they may be defined within the same block. Like if this is a C program and I have got a block like this where this x and y variables have been defined, then in this part of the code it is very much likely that it will be referring to the variables x and y. So, if I can somehow make this x and y easily accessible, then my compilation speed will be better, okay, because I do not have to search the symbol table, the entire symbol table need not be searched. So, searching the first few entries itself, so we can get the x and y variables. So, this is due to program locality, because due to the locality, so it is very much likely that the variables which are defined in the most nested block, so they will be referred to more often compared to some other variable. Like there may be a statement like say x equal to y plus z, where z is a non-local variable, but this is the chances are less because it will be accessing the local variables more. So, scanning the most recent entries first, it will probably speed up the access process. As a result, the compilation will be easier, will be faster, and a variable defined just inside a block is expected to be referred to more often than some variable than some earlier variable. So, this is what I was talking about, that in that x equal to y plus z. So, in that access you see two local variables are accessed and one global variable is accessed, one non-local variable is accessed. So, as a result, most of the time it is accessing local variables. So, we should do something so that these most recent entries they can be searched very easily. So, this is the variation of linear list, which is an ordered list. So, it is a variation of linear tables in which list organization is used. So, this is the list organization, a list is sorted in some fashion and then a binary search is used for log n time. So, sorted in, so if you are sorted in some fashion means it may be based on the name of the symbol, you sort them on the ascending order. Then if it is so, then as you know that once the array is sorted, so we can use binary search and that binary search takes order log n time. So, that way it is easy. However, the problem comes when we are trying to do insertion, because insertion it has to be made in ordered fashion. Like if I have got say in the symbol table the symbols, if we have in the symbol table the symbols like say AB and AC, okay, and then suppose I want to insert a new symbol AA. Then the difficulty is that you can, so you cannot insert AA at the end, because then this sorting order will be lost. So, what you have to do is that you have to have AA at the beginning followed by AB followed by AC. Now, for doing that, this AC and AB they need to be copied down by one position, making the first slot free, and there you can insert this AA, so that it becomes like this. So, as a result, this insertion becomes order n time, whereas search becomes order log n time. So, this is the trade off that we have to do. So, it is insertion is made more costly, so that this search becomes easier. A variant which is known as self organizing list. So, neighborhood of entries are changed dynamically. So, you will see how is it taking place. So, we change the, so that as and when these variables are accessed, so local variables, so they are neighbor to each other. So, that way we can have some better access method. So, we will see how this can be done. So, this is an organization of this is an example of self organizing list. So, you see, suppose in so first we consider this particular figure, this figure A. In this figure A, identifier 4 is the most recently used symbol. So, we keep track of the sequence in which the symbols have been accessed. So, there is a pointer first, or that points to the last referred symbol. Okay. So, in this case identifier 4 is the most recently used symbol, and before that it was identifier 2, and before that it was identifier 3, before that it was identifier 1, and before that it was identifier 5. That means, in my program there was a sequence of access, like in some lines I accessed identifier 5, after that I have accessed before this identifier 5 identifier 1, then after some lines I have got this identifier 1, then after some line I have got this identifier 3, after that I have accessed identifier 2, and then identifier 4. So that this identifier 4, this is the most recent one. Before that we have accessed identifier 2 in this statement, before that we have accessed identifier 3 in this statement, then identifier 1 in this statement, and then identifier 5. So, so this is the current sequence. Okay. Now, suppose after this, what is the advantage, like by program locality, it is expected that in near future we will be accessing in this order only. So, it is more likely that identifier 4 will be accessed compared to identifier 2, and identifier 3 will be, the chances of accessing identifier 3 is even less, identifier 1 is even lesser, and identifier 5 access probability is least. So, that is the expectation, and that happens due to program locality. Now, after some time, so if identifier 5 is accessed, so here suppose so identifier 5 is accessed, then this list will change. This first pointer comes to identifier 5 and this points to identifier 4. From 4, so remaining part remains unaltered. Okay. So, that they are remaining unaltered, and we are just remembering last 5 accesses. So, this identifier 5 access, so this particular link is lost because we are just remembering last 5 accesses. So, that way we can have this this list modifier. So, at any point of time when you are doing compilation, so this first pointer points to the least recently referred symbol, and then successive pointers. So, they will be referring to the previously accessed symbols in that order. So, program locality, so it will say that it will have the expectation that during compilation entries near the beginning of the ordered list will be accessed more frequently. So, this ID 4, the ID 4, ID 3, ID 4, ID 2, ID 3. So, they are supposed to be accessed more compared to ID 5, but here the example that we have taken. So, it is slightly non-intuitive, and is all on a sudden instead of identifier 4, 3, 2, identifier 5 has been accessed. So, that can happen because it is not mandatory that program will always follow the locality of reference. Sometimes it does non-local reference also, and here it is done in identifier 5, and as a result this list gets reorganized. But after that, so it will be now it is having in figure B. So, we are having the situation where the least recently accessed symbol is pointed to by the first pointer. So, this way it can improve the lookup time, because I do not I can search this local identifiers much more faster compared to non-local identifiers. Okay. So, next we will be looking into another type of organization, which is known as tree organization. So, each entry represented by a node of the tree. So, here the entries are same, like we have got the name of the symbol, then we have got its type, its offset, etc., but instead of putting them on a linear table, so we are putting them in the form of a tree, and based on string comparison of names, entries lesser than a reference node are kept in the left subtree, otherwise it is on the right subtree. So, if you look into the tree at this point, you see that root is x, and then the symbol ABC. So, symbol ABC should come to the left side of x, because when you are doing a comparison, the first characters are compared. So, x is compared with A, and since x is if you look into the corresponding ASCII codes, then x ASCII code is more than A's ASCII code. So, as a result x is taken to be greater than ABC or ABC is taken to be less than A. So, as a result this ABC is put on the left subtree, and similarly y is greater than x. So, y goes to the right subtree of x, and then when it comes to L1, so you see that L1 L, so L is less than x. So, it comes to the left subtree. Now, this node has got the symbol ABC and this L is more than small a in terms of ASCII code. So, as a result L goes to the L1 goes to the right subtree of ABC. Similarly, here when Z comes, so Z is greater than x, so it is in the right subtree of x, then the compared with y it is greater than y. So, Z is ultimately put in the right subtree of y. So, now if we have got a new symbol coming, for example, suppose there is a symbol say P. Now, where will it go? So, P, so it is less than x, so it will come to the left subtree of x, then it is ABC. So, A is greater than, so P is greater than A, so it will come to the right subtree. Right subtree has got this L and this P is less than L. So, P will come P is greater than L. So, P will come at this point K L M N O P. So, P is greater. So, P will come to the right subtree. So, that way these new symbols will be put into the symbol table, into this tree type symbol table. So, what we are doing is we are maintaining some structure which is known as binary search tree. So, we are maintaining this structure of binary search tree such that the nodes which are less than the root node. So, they will go to the left subtree, and nodes which are larger than the root. So, they will go to the right subtree, and this process will go on recursively. Now, lookup time, average lookup time will be order log n, because there are if there are n symbols and it is perfectly balanced, if this tree is perfectly balanced, then there will be log n such levels. Of course, there may be a situation where these symbols are such that they give rise to a tree like this. Suppose I have got the symbols coming in this sequence A, B, C, D like that, such that successive symbols are all greater than the previous symbol. So, this will create a tree like this, and in that case complexity instead of being log n, so this will become order n, such complexity will become order n. But for all practical purposes, so this will not happen, because we will be getting symbols such that we get the left and right branches both, and it becomes more balanced. And if it is not balanced, then there are some techniques by which you can do this balancing, which is known as height balancing. I will suggest that you look into some data structure book that will be talking about this height balance tree and all. So, proper height balancing techniques can be utilized, so that this complexity of this lookup can be made to be equal to log n. So, this way we can take help of this tree type of structures. Next, we will be looking into another structure which is known as hash table. So, hash table, this is useful to minimize access time. So, it is the most common method for implementing symbol tables in compilers. So, what is a hash table? So, hash table is something like this, like suppose I have got some symbols, some numbers, let us work with some numbers, say 45, 61 and say 95. So, these are the 3 numbers, and what we do, we take so if this is, so we take a function h of x, which is x mod 11. Okay. So, 45 mod 11, so h 45 will give me 1, okay. Then h 61 will give me 6, and h 95 will give me 7. Okay. Now, if it is like this, then we can, so what we do in that table, we have got entries running from 0 to 10. If it is mod 11, so that entries will be running from 0 to 10. So, in the 0 slot there is nothing. In slot number 1 we have got 45, in slot number 6, so these are all empty, at slot number 6 we have got 61 and at slot number 7 we put 95. Okay. So, advantage is that now suppose I give you a number and ask whether it is there in the table or not. Okay. Search for a particular number. So, but any particular number is given, so say y is a number given as a question. So, what we do? We apply the h function on y to get y mod 11 and we need to come to the corresponding index. So, if this value is equal to say k, then we look at the kth entry into this table. So, if this number is there, if the number y is there, as per our policy, the number y will be in this slot only. So, as a result, for searching a number, I do not have to go for a sequential search through this entire table, I can do it in constant time. So, this access can be made constant time. However, the difficulty with this type of organization is that there will be many slots which are empty. So, in between there may be many empty slots. So, that is one problem. The first problem is empty slots, because depending upon the this mod value that we have got. So, I will get array indices in that range, table indices in that range. So, many of the entries may not have the corresponding values there. And second thing is that there can be several numbers which fall onto the same index, like say so if I have got say 56, suppose the next number given is 56. So, when I apply this function, so h of 56 is also equal to 1. So, I need to store two numbers here now, 45 and 56, but that is not possible because every slot has got a single number. So, this is known as the problem of collision. So, if you look into the data structures, and there are some techniques by which you can resolve these collisions. So, so what you can do, maybe we store 56 at the next free slot, okay, the next free slot that is available, or what we can do is that we can we do not put the numbers here directly, rather we make a chain where we put these numbers on a chain 45, 56 like that. So, these are known as collision resolution techniques. So, we resolve collision like that, and then if we are doing like this. So, when we are putting this number of the next available free slot, so this is called open addressing, this collision resolution technique is called open addressing, and the other one where we are putting them on a chain. So, that technique is known as chaining. So, both the methods, they have got their overheads, like we have got this thing, we need to somehow search through this chain or search through these entries. Okay. So, till for example, if the question is say 56 and we have used say open addressing. So, 56 is here. So, applying the hash function will come to slot number 1, and then we have to go on searching from this point and come back to that entry. So, if the number 56 is not there, then we will be searching for the entire table and we will not be getting it. So, that at that point we can declare that the number is not present in the table, but it is a bit costly definitely. Whereas, but it is very much likely that if the number is there, then you can get it within a very short amount of time, and chaining is slightly better than that. The difficulty that we have is with the deletion, because if you want to delete an entry, then how do you delete it? How do you say that this particular slot does not have the number? So, we need to have another flag here, that which we call say deleted flag, and that flag has to be turned on if a number is deleted. If a number is not, if this particular table entry is not containing a valid data, then the deleted flag should be on. Now, so for symbol table, so this is not a big problem, because for symbol table we can just have this deleted, we can have the deletions are very less. So, we have got only mostly insertion and search, and the search is the most important operation in symbol table, and if we have got a hash table type of organization, then this search can be done very fast. So, that way, that is why this hash table based symbol table organization is very popular, and it is used in many compiler designs, so that when there are large number of symbols and the symbol table is very large. So, instead of searching through the table in linear or binary search fashion, so it is better that we organize them as hash table, and in constant time we can access the individual entries from the table.